Hi, welcome to the video solution for physics past paper. This is Edexcel IAL physics new specification and a second video of a specimen paper for unit 2. So let's start. Question number 16. Sensor Sensors that monitor the moisture in the soil can be useful to farmers. The sensors include two probes as shown in the photograph. The probes are pushed into the soil. This is the probe and some graph is given. X-axis moisture content and resistivity on the y-axis. Okay, so this is some conditions and graph. The graph shows how the resistivity of soil varies with moisture content measured as fraction of volume of soil. Show that resistance of the soil between the two probes is about 21 kilo ohm when the moisture content is 0.14. Length of the soil between probes is equal to 5 centimeter and the effective cross-sectional area of soil between probes is 5.8 centimeter square. So we need to find resistance and because we are given resistivity graph and area and length is also given, so we are going to use formula of resistivity to figure out resistance. So that means we need resistivity of the soil at moisture content of 0.14. So we need the graph that was given in a previous slide, and this is the graph. And now if you see, the moisture content is 0.14, which is on x-axis. So as per a scale, this is 0.11, 12, 13 and 14. So now you can find the respective value of resistivity here, and this is 240 ohm meter. This is the resistivity. So the resistance is given by the formula R is equal to rho L by A, and you just substitute the value. So rho is the resistivity that we found as 240 ohm meter from the graph into L, length. So length of soil between the probe, 5 centimeter, and you need to convert the centimeter into meter. Don't forget this. So it will be divided by 100, so 0.05 meter divided by area. And area is also given in centimeter square, and you need to convert into meter square. So you have two choices. Either you do 5.8 divided by 100 square, or simply you just replace the prefix centi from this value. That's what I am doing. So I am writing area as 5.8, and I'm removing this prefix, which is centi, 10 to the power minus 2, but I have a square on centimeter, so I just write square. So that's how we can convert centimeter square into meter square. And when you solve these numbers, so R would be equal to 20689.655, and then you shift the decimal on left hand side 3 digits, so R would be equal to 20.7 kilo ohm, and this is approximately around 21 kilo ohm. That's what you can find the resistance. The sensor consists of a circuit that includes the probes and provide an output potential difference as shown. The output potential difference can be used to switch on a water supply. So this is the probe here, and this probe are connected with some resistance, and this is 0 volt potential difference and 5. And if you see this, this whole circuit is basically a potential divider in which we use two resistors in series connected with some power supply. So Now you see here. So this is the simplest circuit of a potential divider, resistance R1 and R2. And how can you apply this concept here? So this is one resistance, 129 kilo ohm, and another resistance is the resistance of the soil, which is here or here. And the total power supply or power supply voltage is 0 to 5 volts. So this is your power supply voltage. Okay, so what are they saying now? Calculate the output potential difference when the resistance of the soil between the probe is 21 kilo ohm. So you need to find voltage across the soil. That means you need to find that voltage. Let's call this voltage is V1. And you know that because we are given a total power supply voltage. So we can use a formula for potential divider, which is V1 is equal to R1 divided by R1 plus R2, which is total resistance of the circuit, into power supply voltage or voltage of the source. And you can apply this approach in this first part of the circuit. So V1, which is the voltage across probe, is equal to R1 is the resistance of the soil here, and this resistance is given as 21. I'm not writing kilo. The reason is because kilo from numerator and kilo from denominator will be cancelled, so don't need to write. So 21 is equal plus divided by this is R1, and R1, which is 21 plus 29 into 5. And if you solve this, so your answer will be V1 would be equal to 0.7 volt. That's how you find the voltage across the probe. A farmer finds the following notes about the sensor on the internet. If the output potential difference falls below 0.7 volt, then this indicates that the soil has a moisture content of less than 0.14 and the water supply is switched on to make the soil water. Discuss whether this information is correct or not. Now, if you recall the circuit, and this is potential divider. So what happened if we found that the potential difference between the probe is 0.7. Now, what if I say the voltage is decreasing? So if the voltage will decrease only if the resistance between the probe is going to change. And as per graph, what is happening, if you see the graph trend, so moisture content decreases, so you say that the resistivity is increased. This is the pattern of the graph. So this is something like 0.14 that we use, and if the moisture content is decreasing, that means resistivity increases. And if resistivity increases, so if R is equal to rho L by A, so if resistivity is increasing, that means resistance also increasing, and increasing resistance will cause voltage to increase, not decrease. So the statement is absolutely wrong, because it will turn off the water supply rather than turn on. So that's how you can combine all these relation. You can see from here the resistivity, moisture content decreasing, so resistivity increasing. That's how you can write. A different sensor can be produced by replacing the probes with a negative temperature coefficient thermistor. Explain what this sensor circuit could be used for. So it's all about thermistor, and you know that thermistor, the behavior of thermistor is, if temperature is increased, so the resistance will decrease. So for thermistor, temperature increase, resistance will decrease. So voltage across the component will also decrease. So that means if voltage is changing due to some other factor, so this thermistor can be used for some circuit which control temperature or control amount of heat. So that's how we can use a circuit contain thermistor to control the temperature or heating process. So any type of heating or cooling system, we use thermistor. Question number 17. A gold leaf electroscope is used to detect very small amount of charge. The diagram shows an uncharged gold leaf electroscope. This is uncharged. The normal situation of gold leaf electroscopes is, this is a gold leaf and this is a metal rod. This is a metal rod. When the electroscope cap is given a negative charge, electrons spread along the metal rod and the gold leaf, so both become negatively charged. The rod and the leaf repel each other so that gold leaf rises up as shown below. And this is the principle, working principle of a gold leaf electroscope, because if you give negative charge, so all the electrons from this metal cap goes down, and this is all made of metal, and it spreads all over the metal and the gold leaf. So due to same charge, they repel, and we see that we have a more deflection in the gold leaf. That's there. This shows that it has same charges, whether negative or positive. So a gold leaf electroscope can be used to demonstrate the photoelectric effect. A clean zinc plate is placed onto the cap of the electroscope, and the plate and electroscope are given a negative charge. Ultraviolet radiation shown onto the zinc plate, and the gold leaf slowly falls. Explain why the gold leaf falls. So the reason is, if you see the behavior of photoelectric effect, photoelectric effect is falling of some certain light like ultraviolet light on a metal surface causes emission of electron. So if you have a metal plate, any type, a specific type of metal plate, and some specific light like ultraviolet is falling on the metal plate, so from the metal electrons comes out. And that's exactly what happened here, because a zinc plate and electroscope is negatively charged. That's why you have more deflection in zinc plate. But as ultraviolet light falls upon the zinc plate, so electron emits from the plate. That means amount of charge into the electroscope is decreased. That's why the force of repulsion is decreased, and gold leaf falls slowly. So that's how you can write. Zinc has a work function of 4.3 electron volt. Calculate the maximum wavelength of light that will produce the photoelectric effect with zinc. So we need to find wavelength of zinc. Wavelength means we need to find lambda, and we are given the work function. And remember, the work function is phi naught. So according to quantum mechanics or quantum theory, energy of any photon E is equal to hf, and in this case this E basically equal to the work function. So this E, which is energy, so you can write phi naught is equal to hf, and clearly we can get rid of this frequency because we need lambda So F lambda is equal to C. So F is equal to C by lambda, and you replace F from here in this equation. So phi naught is equal to H C by lambda, and then lambda would be equal to H C by phi naught. So now you can see that H is Planck's constant, which is given in the formula sheet. C is the speed of light, also given there. Phi naught is a work function, which is given in electron volt. So before substituting this 4.3 into the formula, we need to convert this electron volt into joule. Don't forget, electron volt need to change into joule. And how do we do that? So 4.3 electron volt is multiplied with 1.6 into 10 to the power minus 19. Now if you multiply this, then this will be in joule. So this is phi naught in joule. And now everything you have, so you just substitute the value. So you say that lambda is equal to H. H is Planck's constant, which is 6.625 or 6.63 into 10 to the power minus 34 into C, speed of light, 3 into 10 to the power 8, and divided by phi naught, which is 4.3 into 1.6 into 10 to the power minus 19. And you solve this for lambda, so lambda would be equal to 2.89 into 10 to the power minus 7 meter, or you round it off, so lambda is equal to 2.9 10 to the power minus 7 meter. This is the wavelength. Part C, the electroscope is charged again. The ultraviolet radiation is replaced by a high intensity source of infrared radiation, and demonstration is repeated. The gold leaf does not fall. Explain why the wave nature of electromagnetic radiation cannot be used to explain this observation. So reason is, according to electromagnetic wave theory or theory of electromagnetic wave, the wave theory of light, the energy of radiation depends on intensity. So the theory suggests that if you increase the intensity, this is as per wave theory. So wave theory suggests that if, because energy, let me just, because energy of wave depends on intensity of the wave. So if you increase the intensity, so energy should increase. This is the wave theory. So it is said that if intensity is increased, so we can assume that the energy of incident radiation is also increasing. So electrons should be emitted with high energy. But in fact, in photoelectric effect, in intensity, it is not observed here. It is not observed. If you increase the intensity, so only number of electrons are increased, energy stays the same. So it doesn't matter if you are replacing the ultraviolet with some other source of light, or infrared, which of course infrared has a less energy than ultraviolet. But if you are even increasing the intensity, so intensity will not affect the energy of the radiation. So energy stays lower than the ultraviolet. So that's why electron do not emit, and the gold leaf does not fall. Question number 18. The concentration of sugar in fruit juice can be determined using a refractometer. A simple refractometer consists of a 45-degree prism made of glass. Calculate the speed of light in the glass. Refractive index of glass is 1.52 meter. So sorry, it's not meter, it's just refractive index, so 1.52. So you need to find, because you are given calculate the speed of light in glass. So we have a simple formula: n is equal to c by v, where c is the speed of light in vacuum or air. If you don't compare vacuum and air, so speed of light in air is as same as speed of light in air. So c by v, v is the speed of light, is the speed of light in glass. So n equal to c by v, and v is equal to c by n. You just replace. So c is the speed of light, 3 into 10 to the power 8 divided by n is 1.52. So v is equal to 1.97 into 10 to the power 8 meter second inverse. That's how you can find the speed of light in the glass. Part B, the diagram shows the path of a beam of light traveling from a light source in air through a 45-degree prism. The path taken by beam of light is shaded. The critical angle for glass is 41 degree. Explain the path of the beam of light. So why do we have these path? So basically, if you see that we have a light coming in some spreading out from the source, it is not coming in just a single path, so it is spreading out. And now if you see what is happening, if you see the beam of light coming at that point, like you can see, it is something like this is the ray of light coming, and some ray of light will be, after bending, they will be reaching here, something like this, you can imagine. So if you just recall the boundary or normal line at all these points, so at this point you have a normal here, something like this, and here you have a normal. So you would have normal at all the point, like some light will be coming at that point, light will also be coming. Now if you see at that point, the light will be coming something like this, and then something like this. Maybe you see here it's bending. Now as you are coming down along the boundary, so you see incident angle is continuously increasing, you see here. So for those beam of light which are some sort of you can say above some point at above region of the prism, so here incident angle is less than the critical angle. So in this region you can imagine the light will be refracting, and after refracting it will be bending away from the normal. But approximately in this region or at all the points, you can imagine that the incident angle is greater than critical angle. So you have a total internal reflection. So as per this shaded region, you can imagine that at these points, this lights are totally internally reflected, and this light some point here like this. So this is refracting due to less incident angle. So that's how you can explain the whole path. Part C, a sample of fruit juice is placed on the prism. The initial path of the beam of light is shown. Some of the transmitted light falls onto the scale. Some light falls onto the scale. Show that critical angle of light passing from glass to the fruit juice is about 59 degree. Refractive index of fruit juice is 1.3. So we have a refractive index of juice 1.32, and then we have a refractive index of the glass because we have a refraction from glass to the juice. So in previous part we have a refractive index of glass which is 1.52. So we can use a straightforward formula: n1 sine theta 1 is equal to n2 sine theta 2. So n1 is the refractive index of medium 1 and theta 1 is the angle in the medium 1, while n2 is the refractive index of medium 2. Theta 2 is the angle in the second medium. So the first medium is glass. So you can say if you have a 1.52 and sine of theta 1, that's what we need to find, sine 1 theta 1, which is because we need to find critical angle here. So sine 1 theta 1, and then is equal to n2 is 1.3, which is this, and sine 90 because we need to find critical angle. So theta 2 should be 90 degrees. So you can say sine 90 because it's a second medium after refraction. And you just make subject as theta 1, you can figure out theta 1 here. So if you rearrange for theta 1 would be equal to sine inverse 1.3 divided by 1.52 because sine 90 is 1. So 58.78, which is approximately 59. So theta 1 is equal to 59, which is a critical angle. So this is in fact critical angle because we choose 90 degree as a refracted angle. Okay, add to the diagram to complete the path of the beam of the light. Okay, so you need to complete the beam of the light. Now you see again what is happening here. So refractive index of the of juice is 1.3. So what happened here? At some point the light will be refracting as usual, but at some point, because it is not air now, so we have a less difference between the refractive indexes between the two medium. So you can imagine some light will be coming from here, something like this. It is totally internally reflected, and some light is also again coming from here, something like this here. And then after that they will move away from the uh, you know normal. So you can imagine something like this, and then again something like this, and then some light will be bending, moving inside, like you can imagine something like here. That's how you can complete the path. Okay, that's how you can see. Juice containing a higher concentration of sugar will have greater refractive index. Of course, if concentration is increased, so refractive index is increased. Explain how the length of the scale that is eliminated will change if this fruit juice is replaced with the sample containing a higher uh, concentration of sugar. So if concentration of sugar is increased, then refractive index will be increased, and that will cause theta to increase. That means the incident angle will be more. So there will be very less total internal reflection. So the illuminated region will be less on the scale. Thank you very much. I hope you understood this paper. See you in the next one.